So yeah, thanks for coming, everyone. Today, yeah, as Chase said, I'm going to talk about this project I started called the Ames Stereo Automated Pipeline. So you can see the sort of logo right there, which I'll explain in a moment. I should say, though, I'm a fifth-year PhD candidate at Johns Hopkins in planetary science, and a lot of my day-to-day is studying sedimentary deposits on Mars using HiRISE and CTX stereo products. So I use Ames Stereo Pipeline a lot for my work, and sort of over the years that sort of necessitated some sort of like streamlining of the work to make it easier, and I'll get onto that. So yeah, title slide, there's my Twitter, there's my website, all good. So for those who haven't interacted with the Ames Stereo Pipeline, I kind of mentioned it, it's been mentioned a few times. What is it? It's a open source software toolkit, and maybe Ross Beyer will chime in as I butcher this, but it's basically a software toolkit used to produce digital elevation models, DEMs. These are 3D point clouds to sort of rasters where each cell value is elevation, right? Because you want to look at your topography, look at your landscape, measure thicknesses of things, measure volumes, that sort of thing, plan traverses for rovers. So it's kind of like a workhorse of the planetary science, like, mapping and geology toolkit here. And it's been around for a number of iterations for a while now, actually. But what's great about it is it's free and doesn't require a user to sit in front of a stereo monitor for hours and hours on end. It kind of can, if you script it right, can kind of just do its thing with minimal sort of user monitoring. And yeah, it's free. So, anyone can download it, anyone can run it. And I'll start with like this little quick little video. Hopefully this works. This is a example DEM I made in HiRISE data of a outcrop of layer deposits in a crater called Caporo on Mars. It's in northwest Schiaparelli Basin. It's actually right near one of the traverse paths of Mark Watney in The Martian. Let's see if I can't do that again, because it shows you meaningless ads. Anyway, so this is like the sort of product you can imagine. Like, I'm very zoomed out, but you can see there's a lot of detail here, because in the end, the HiRISE is a 25 centimeter, nominally a 25 centimeter per pixel imager. So you get nominally 1 meter per pixel resolution in your elevation model. So that's the sort of products you can make with this pipeline. So then we can sort of move on to how you actually use the Ames Stereo Pipeline just briefly. Like overhead, it's a lot of steps and doing things in Bash and a lot of commands. So what you end up doing, and some of these commands can run for a while, like a couple hours on a single computer, which is sort of the way I typically use it. You can accelerate it on a Slurm cluster, but certain steps will take an hour or two just because of them being single threaded, or for whatever reason, even just downloading the data can be slow at times. So there's like a lot of steps involved, and you have to run them in the right order. And occasionally you have to go back and rerun a step, and you're like, okay, which step did I run? Which parameters did I use? Did I forget this or that flag? And it becomes sort of like a hard thing to solve. And for people who don't like sort of live in Bash every day, it can be difficult. So one of the other motivations for making this sort of wrapper project that sort of makes this, sort of greases the wheels and makes this all a little bit easier, is that other people wanted me to make dems for them. And it's like, well, how about you make your own dem? But it's all good. But then there's other issues, like you'll see, like in the literature, people publish DEMs. I say DEM, and that's a DEM, that's digital elevation model, just again, to alliterate that. But you don't know necessarily what parameters they ran with Ames Stereo Pipeline, what they use, so you can't reproduce that work or make it better or anything else. So that's sort of like, I think that's like one sort of cool outcome of this, and we'll get more into technical bits and the really cool Python parts, and that's going to be the meat of this talk. But I think like a key takeaway is that, and as we're seeing this whole presentation is done in Jupyter notebooks, you can use Jupyter notebooks as this sort of workflow, like serialization format. You can define your various jobs, like various Python, various Bash jobs, all within Jupyter notebooks, and when they run, you save all that output. I was saying something about parameters, and there's a lot of them, so we're just gonna scroll briefly through this. This is a Ames Stereo config file. A lot of these like hashtags, those are comments, so they're not really consequential, but you can sort of get the feel for like the sort of thing you may have to deal with if you're using Ames Stereo Pipeline a lot. There's a lot of these parameters, and some of them are for certain steps and not for others. So you have to manage that and also remember what you ran with what DEM and like what you did. So, or changing things to fix various steps. So the inspiration for this project was something that the initial effort, and Siri thinks I'm trying to talk to Siri, was a project called the ASP scripts by David Meyer at Edwin Kite. And it was a series of bash scripts that sort of just do this thing. It wraps a workflow to go from end to end from, I just have two CTX or high-rise images that I want to make a DEM out of, and it'll just do all the steps. And it was really great, and it used Bash, so like it's sort of like it is the inspiration for this workflow because I'm re-implementing that workflow in my project. However, because it's Bash, it's a little inflexible in places. If a step ran, like the whole script may take a day to run, but if one step in the middle sort of failed, you would have to go back and like figure out what ran, and we'd have to like re-execute Bash parts to get those parameters out. So it just wasn't flexible enough for me, my things to talk about a bit more. This is their poster from LPSC 2016. This illustrates from left to right the various steps that you have to do, and it's great. Like they basically reduced it down to one or like a handful of steps to go from end to end. Their workflow involves first producing a CTX DEM that's then aligned to MOLA. So then you have really good control on with a reference DEM from which you can then produce a high-rise DEM, align it to that CTX DEM. So you get this sort of pyramid stacking where you have MOLA elevation data, you have CTX elevation data that's aligned to it, you know, very well, and then high-rise to that. So you're able to position your high-rise correctly in three-dimensional space. So that's sort of the motivation for even making a CTX DEM when you're interested in high-rise, but it's also good for context and mapping, and there's plenty of other scientific use cases for just using CTX. So how do we reduce some of these pain points? And that just leads straight on to what Ames Stereo Python Ames Stereo automated pipeline is. It's just a reimagination evolution of the ASP scripts into Python, where I've re-implemented things using some key Python libraries that make it really tractable to do this, and sort of represents a stack of Python libraries. And I'll go through an advertisement bit here to sort of show each of them, but you can sort of see it's just like, you know, Python is great glue, so it's used Python to glue things together. Yeah, let's just get going. So because this is a Jupyter, I can just run Bash in it. So this is a quick demo. I'm not going to do anything fancy. I'm just going to show it's working. So boom, there it is, like Ames Stereo. I have a command line tool that wraps my Python code using a project called Python Fire, which I'll explain in a bit. And it provides these workflows into the command line, and also into Jupyter notebooks, and also as a Python API, all without additional code. So it's really flexible and powerful, and I'll explain sort of what's gluing these together. Again, I was saying some great Python libraries, so here's some to jot down. The first is Python Fire, sometimes just called Fires by Google, but it will take any Python class or function and directly turn it into a command line interface with, you know, 2 lines of additional code, maybe. And you can even like turn anything that's already like pip already installed in your Python environment into a command line tool. So it gets really creative. These are just some quick little examples from their docs where, okay, they made a little like calculator app. But it's a lot more flexible than I'm leading on here, because I have to move on to the next like key enabler Python library. Another one to write down is sh. Kind of hard to Google. You have to like type out sh.py. That's sort of how I find it. But it automatically turns any program that's on the user's path into a Python function. So their quick example here is running a standard Unix command called ifconfig, passing in parameter, and it'll work. So I can just like run that now. Anything that's on the bash path, anything that's on your path can be executed. Even things that are not, you can directly say, I want to run this executable that's located at this directory. And so automatically, without doing any coding, I already have access to Ames Stereo Pipeline. Parallel stereo is one of the command line tools that's already provided in Ames Stereo, and I was able to execute it and get output out. So that's like one of the key ways I actually am orchestrating everything in the Python code, is just using SH to call things out. And what's even nuts is, right, I can, like my own tool, which is installed as a command line tool using Fire, as we just saw, I can even use it as as a Python function, even though you could just import it. But anyways, it's just to show that that works. This next one is Papermill. Papermill takes Jupyter notebooks and allows you to parameterize them and then run them from the command line. This is being used by, I think, like groups at Netflix and sort of data science like areas where people tend to want to work in Jupyter notebooks, but then how do you productize your Jupyter notebook into a thing that that can run and isn't just like dead code sitting in the Jupyter notebook. So Papermill basically is, all it takes is a little metadata at the top of your Jupyter notebook, and you can specify commands that at the command line. This won't do that, but it's just to show that Papermill is a thing that's on the path. You can take that notebook and run it with options that you provide, and then it'll output the resulting notebook after that runs for you to view as a sort of log. If you're not familiar with Jupyter notebooks, they're similar to, I think it was Mathematica had something similar. It's a field, it's a sort of tool that's in the sort of iterative programming universe. That might be the umbrella term for what notebooks are, but essentially we're looking at a notebook right now. Like you've been looking at a Jupyter notebook this entire time, but it lets you create little cells that you can run code in or write documentation in Markdown and et cetera, or integrate HTML and like PDF viewing. So it's a really dynamic sort of cool thing. And I can save out this presentation as a notebook file and you can run it yourself if you were so inclined. The next little project is a small little wrapper I've also written called Moody, which uses the ODE REST API. That's the orbital. Actually, I forget the acronym, but it's the Geosciences PDS node at WashU St. Louis. And they provide a REST API that's a web-based API that lets you download data, query metadata about images, that sort of thing. And it made this little quick thing because I wanted to download images and such, or get metadata on images that I knew. So there's some commands for that. So that's one of the key enablers. So sorry, that was a lot of things, but those are all neat little projects that sort of combine together, make are more than their individual components, more than the sum. They're more than the sum of their parts. Like that increases. So is ASAP a command line tool, a Python API, or a notebook workflow? It's all the above, because as we saw earlier, although you can use ASAP through the command line interface that we were just looking at, one of the key advantages is I've also include Jupyter notebooks that then call in each of these cells, and we'll run through a demo of this like pretty shortly. Runs through all those steps in the order you need them, and we'll output those, and you can use the command line to start a notebook, have it run in the background, and make your stereo product and have all the logs saved. So it's sort of, ASAP is sort of combining all these things to make it really easy to produce DEMs, to make all the calls you need to Ames Stereo, to go back and fix things as they go wrong, or just to automate it so you're not watching the paint dry a bit. And it could be integrated into other tools fairly easy. So again, I'll just quickly get through this before going on to the main demo. But there is like a high level command called ASAP, which has some groups and other commands that you can run. These are some of the older actually versions of the steps that are orchestrated into 2 or 3 steps sort of naturally. But for example, there's the CTX side. So these are all the steps necessary to produce a CTX pair, DEM pair from start to end. So that's all those steps enumerated. There's a common utilities that has like some things that are useful probably to other people, but some things that are kind of just generic, and is leading to some code reuse, because a lot of the pipelines between LRock and CTX and Highrise, you're going through a similar workflow between ISIS like pre-processing and then feeding things into Ames Stereo Pipeline. That would just lead to different ISIS commands being called as needed. But by writing in Python, you can do it in such a way that you're able to reuse code, and that simplifies maintaining this project. But there's still some work to do there. And then for each of these functions, again, I didn't write any like art parsing things. It was just all Python Fire doing it for me. Like I can get a help like print statement for one of the functions in the high-rise pipeline, and is taking my doc strings from the function and turning them into this neat little help document. You also get tab completion through Python Fire. And then again, because this thing is a Python project, I can use it directly as a as a Python project if I was so desired. So again, I guess yes, jumped the shark a bit with describing why notebooks. But just to reiterate, the literate programming enables these reproducible workflows. Again, your parameters, such as which images you're interested in, could all be parameterized and then saved in a file. And then I can hand my notebook to someone else and they could run it to produce the same product, hopefully. That's sort of a big unknown, and is a big increasing issue in science, the reproducibility issues. I think we've seen it in other fields, and it's going to become a problem eventually in planetary science if it isn't already. So this doesn't solve that problem, but it hopefully starts at helping to take a crack at solving that. So in the future, like future works, like someone could probably make a Docker container that has Ames Stereo Pipeline and ISIS and ASAP in it, and you would just sort of use that to produce the DEMs for a publication, for example. So you could show that, okay, well, maybe it's not using the latest and greatest ISIS or something, but it'll at least recreate the DEM products used in the publication as one example. One kind of neat thing is, like, because it's on GitHub, I was using a GitHub action, and I'm not going to scroll through all of it, to even do unit testing of the workflow. So we'll run a little GitHub action and run that. So that's kind of the bulk of the talk. And now I can move on to the demo. Yeah, the summaries, I think, yeah, that's all good. So let's see one of these things in action. Now, this is going to take a few minutes. So what I think, I'm going to start it, and I'll like reopen my chat window. And then I can start to take questions, and as it progresses, we can sort of watch it go. So I'm going to restart and run all cells. And hopefully I'm on the right kernel. Yes, I am. Restart. All right. So, well, hold on a second. I probably need the chat up. And how on earth do I do with them? Man, I don't like to Zoom that much. Well, hopefully there's, okay, there's participants list, so I'm getting closer. All right, well, I'll talk as maybe Chase can MC some questions for me. But this is literally one of the notebooks that are sort of contained in the project that's sort of reproduced here, and just, it's running. So the way Papermill works is you define a cell at the top of your notebook that has all the parameters enumerated. And this is the result after having run it from the command line. It will insert those parameters like into the output notebook. And I just copy that output notebook and then place it here to sort of rerun. Some parts are inserted here just to make it a quick demo run, and we can, hopefully things are still happening. Anyways, I'll be catting out the stereo config file, so it's preserved in the notebook for posterity. Doing some quick Python things, like you could like sort of have these go to some folder that you always want them to be rendered out at. By default, it goes to the current working directory. Okay, so yeah, that explains it. It's currently downloading the CTX data still from the PDS. So that'll be over momentarily. So okay, there's boom, it's gonna go. Now I can hear the computer running. We can see all the cores moving. So that's all good. And I'll start talking through the steps. So like the first step was just downloading the images. And the only thing that's required for that, you need, this is really just goes down to particulars of even how you make a DEM. You just need two overlapping like images that one image is presumably more native than the other one. Ideally, you would have something that's completely nadir, you're staring straight down, and then a side-looking image that's maybe 10, 15 degrees off from nadir. There's a LPSC abstract that I'm forgetting the title of, but it's sort of about like the optimal parameters to use, but not important. Anyways, you have 2 images, you need to download them. That's the more important thing. And then step 2 is just running through a lot of ISIS commands to sort of calibrate the data and get it in. I think someone is waiting to chase our go. Okay. Yeah, I still can't see the chat, so I don't know what to do about that, but we'll just keep going. So, that's
there have been no questions.
Okay, great. So people are just wowed, I'm hoping, or bored. So yeah, step 3 just does some metadata stuff. I rescale it to just make this run faster. So I'm reducing the actual size of my DEMs, or sorry, of the source CTX images to 1/8 of their resolution. So I'll just make this all go really quickly. And step 4 is the bundle adjustment, which is sort of refining the spacecraft position. It doesn't have ground control points or other things to sort of do a good job, but it does a good enough job to reduce some of the errors. So that's just running, and that'll take another minute or 2, I think. And then we'll see step 5 and 6 is when it actually starts doing the stereo correlation. And what's also cool in the notebooks, as I sort of preview what's going to happen in a few minutes, is that after these sort of steps, like when there's images to view that are useful for diagnosing what's happening with your stereo run, it will actually render them out into the notebook. So what I commonly do is I run Ames Stereo on some remote computer over SSH that I don't want to X forward to, but it's pretty easy to port forward for running Jupyter on that remote computer, and then just using your web browser. Thanks, Siri, so useful. Just using your web browser as your sort of GUI to interact with the system. Because I have Bash over here in the terminal, and all of Jupyter powers here. So yeah, it's starting to run the stereo right now. And you can sort of see those logs happening. Now, it's a great process to watch because there's just so many things like sort of, jumping out in the terminal. It's like a wild progress. But actually, one of the reasons for the projects is to sort of stop the sort of watching the paint dry activity. You don't really need to sit here for an hour watching. Well, this isn't going to take an hour, but for a high-rise image, it could take several hours. So the idea is just to let it run, and then you sort of check back the next day or whatever it should complete. And see if something went wrong. That's sort of the way I would prefer to interact with my projects. So yeah, so that's just continuing to run. And yeah, we're probably looking at another minute until we're going to see some neat pictures pop out of here. I think I think it takes less than 10 minutes, this whole thing. Maybe more like 8, but yeah. It's running, and I think I've talked myself to death, so I'm going to take a drink of water, and hopefully there are some questions. There's the chat. Now I found it. All right, so I see, yeah, Ross, thank you. I think, yeah, that's the LPSC abstract. Yeah, and I have not heard of your other project here, Ross, so I'm curious. I'll take a look at that later. The other thing is, there's one last thing is I do have documentation hosted on Read the Docs. So if you want to get more of a blow-by-blow about what's happening in the notebooks, I sort of do that whole process in here. And you can find the project on GitHub. It's just my GitHub ASAP Stereo _. So yeah, the documentation there's still work that needs to be done on that. I need to still document the high-rise side, but it's fairly analogous to the CTX. It's just sort of time-consuming. Okay, so there's a good question. Do you need to install? Yes. I mean, unless you're not using product like planetary images. If you're using digital globe imagery, I'm guessing you don't. The good thing is I do provide a Conda environment in the project that situation has improved remarkably over the past year. And that was actually like I've been working on Ames Stereo for maybe 2 years at this point, but because of how Ames Stereo was distributed versus how ISIS was distributed versus dependencies, it was kind of a mess to run in the past. So yeah, so to answer Yuki's question, you probably do though, because ASAP doesn't work with, I haven't implemented other workflows like for Digital Globe or something. But if you want to implement a workflow for Digital Globe or something else, like you can just follow the sort of groundwork that's already in ASAP to do that, and that could be a great user contribution and would form its own like component in the API there. So I think the answer is basically yes.
Yeah, if you conda install Ames Stereo Pipeline, it will conda install ISIS for you.
Yep.
So,
Oh,
this is great. Oh yeah, math coming up. But I wanted to ask you, because it'll still be doing things. So if someone is new to creating stereo models and they're interested in building their own, should they come to ASAP Stereo first, or do you think that they need to know how to run Stereo Pipeline in all of its terrible, terrible command line glory and understand that process before they can benefit from the ASAP Stereo project?
I think as currently envisioned, it's more that latter case. Yeah. My hope is that that you do your homework and learn what the stereo pipeline is doing in each of its steps and how the various parameters change things, and that would then enable you to look at the steps that are in the pipeline and see, does that make sense, right? Like you can't just that's something that, yeah, there are with some instructions you can hand it to someone relatively novice, but you still have to know how to work with Bash, and you still have to understand things about ISIS and these other sort of components. And yeah, so I wouldn't call it a replacement, but for Ames Stereo Pipeline users that know how it all works, like I think they can be relatively confident to use. Another feature of the command line, so something I'm not showing because we're not looking at the code, is that in each of these steps, or I think all of them, I also accept all the keyword arguments that the Ames Stereo tools require. So you can override like a lot of things. So like in like point cloud alignment, you can align I don't know, like some of the which like transform you're going to use. For example, I set a default. So ASAP has a lot of sensible defaults, but you can override that behavior. But that being said, like there's some tools that, because it's written in Python, it might make it easier to make things that are easier for more novice users to then learn Ames Stereo Pipeline. Like one thing I've been thinking of doing, and there it sort of finished that first step, and we got the final hillshade and the petter data to do the alignment. So I'm gonna run the next notebook, but to finish my sentence, I've been thinking of making a little script that will let you do a parameter sweep of the stereo config you're using. So you can say, I want to test correlation kernels between 7x7 to 25x25 or something. And because it's written in Python, it's really easy to go, okay, I'm going to go find like a representative patch in the image or just some random patch of area and render out a small little DEM and let the user decide if it's good or not. So I think it's sort of like all this sort of orchestration that it's hard to do that in Bash, or to make that pleasant to use in Bash. So it makes more sense to do it in sort of a notebook like environment. Run all cells. There we go. All right, so this one part will take, this is basically all the second part of this notebook is called the Align DEM notebook, which the title is getting truncated. is doing is just aligning that CTX DEM to the Petter data.
So the first notebook made the DEM. Can you just review what these steps are? And
yeah, they're. Well,
and why are these two separate things instead of part of one workflow? Or
yeah, so I'll scroll back to David Meyer is on the line, so maybe he can chime in. But I'll scroll back to their poster. But basically for CTX, for CTX setup, there we go, the hand wave. So David, if you want to jump in, please, I can take a drink of water for why you want to do that. But in the end, it's just a natural sort of break in the workflow, because to figure out how to align your DEM to MOLA requires sort of a manual step at the moment. But in absence of David jumping in, so CTX, broadly speaking, what's happening is a low resolution DEM is calculated like before map projecting the products. If you map project the products, you can get a higher quality stereo product out of it in the end. Ross can correct me on that. But the idea is to do a low res DEM that reduces a lot of the perspective error to make the alignment smoother. And when you're sort of done with that, you have a DEM that's correct, but it's in the incorrect position in XYZ space. And that's because the way this workflow works, you don't use ground control points because it's like a very manual process. So we just produce a DEM. It'll probably be within a kilometer or two of where it should be. So we then grab the MOLA data using the Petter tracks, like the actual laser altimeter dots on the surface instead of like an interpolated DEM, which I think is illustrated. Yeah, it's sort of illustrated in this figure, which isn't zoomed in. So apologies for that. But in any case, there's a command in Ames Stereo called PC align, which requires at least a notion for how off the 2 point clouds are from each other. So how far away in X, Y, and Z space it is. And it will sort of yell at you if you pick too small a number. And if you pick too big of a number, depending on the situation, things will go badly. And it depends on which mode you're using, which parameters, and these other things. So the safest bet is just to load the Petter data and the sort of initial DEM into a GIS environment. I use QGIS for this. It's takes all of like a minute or two to do this. So you kind of just load the two products in, click on a point, and look at the Z difference, the difference in the elevation between the two, and that'll get you some notion of how big it is, and then you sort of buffer it. I do set a default of like 500 meters, which, because I work in the equatorial region, has worked out pretty well for me. Yeah, and David's, yeah. And if I'm not sure which ones David's referring to. It might be the Hillshade alignment or the N-align program in the chat. GeoDiff. Okay, well, I guess I learned something. So yeah, so like we can, so yeah, new workflow can be pretty easily introduced to just fix that step and make it all end to end. That being said, if it's a high-rise image, that point cloud alignment could take a while. So it's kind of a good step to a good stopping point to also inspect the quality of your DEM and make sure it's not total garbage, which can happen at some point. So instead of like waiting another couple of hours for the point cloud alignment to align a bad DEM correctly, it's kind of a good stopping point. So